welcome to students. Today we will be looking into the population dynamics model. So, it all started in 1970 when Robert May he proposed a mathematical model to study the complex behavior exhibited by the growth of population in certain biological species. So, let us assume that there is a particular space S, and for this particular space S we can observe that the individuals here are they born and they die right within the same year. So, this can be actually observed in many insects and all. So, we start with N0, say for example in the very first year the number of species is N0, then it has been observed that whatever the number of species comes up next year depends on the number of species this year. So, supposing in the next year we have the number of species to be N1, after that here we have the number of species to be N2 and so on. So, he observed that this Ni plus 1 at the I plus 1th year is basically proportional to Ni. So, the number of species in the corresponding the next year will be basically depending on the number of species in the present year. Now, so this gives us some kind of a proportional constant. So, this gives us an equation and we can say that Ni plus 1 is basically A times Ni, where Ni is the constant of proportion. Now, what happens if this A is greater than 1? So, if A is greater than 1, then it is observed that the population in the subsequent years, right, you start with N0, right, N1, N2 and so on. So, in the corresponding years, right, the population tends to infinity, right, and basically the population explodes. So, in this case the population explodes if A is less than 1, then it is observed that what happens to the species is that the corresponding year you will have less number of individuals than the present year, and that continues, and since A is less than 1, it would happen that as time tends on the population gets extinct. And if my A is equal to 1, then the population remains constant, does not matter however the season changes, whatever happens to the year, the population continuously remains the constant. So, population remains constant. Now, it was observed that this is not a very practical model for population. So, what is a practical model for population? So, it was observed that population also depends on how the individuals interact among each other. Say if two people are interacting, right, there will be a competition for food, there will be a competition for shelter, there will be competition for space. So, it also depends on the number of it also depends on the mutual interaction. So, it was observed that we need another constant, we need another term in this model which is proportional to n square, basically representing the interaction. So, it was then proposed that Ni plus 1 should be equal to something like A times Ni minus B times Ni square. Now, what happens here is, why do we have minus sign here? Because as the interaction increases, you can observe a decrease in the population. Now, this, if you look into this model, if my B is very much less than A, then as long as my Ni is very small, the second term is not going to make any difference. But what happens here is that if Ni becomes sufficiently large, so once Ni becomes sufficiently large, Ni square dominates, right, and then that plays into the population in the corresponding year. So, we observe here that I can write my N1 to be equal to A times N0 minus B times N0 square. N2 can be written as A times N1 minus b times n1 square, right, so on. At the nth stage I can write nn to be equal to a times nn, sorry, nn plus 1 to be equal to a times nn minus b times nn square and so on. So, it was observed that you can write, you can look into the corresponding population in this particular manner. We want the population to still remain positive. So, supposing I want my nn plus 1 to remain positive, what happens in that particular case? Then one can observe that simply calculating the stuff, one can observe that in that case my nn cannot exceed what I called it as a n maximum, which happens to be equal to a by b, right. I think that is what it turns out to be, yes, turns out to be a by b. So, if my population turns out to be equal to a by b, right, we can find that this becomes extinct, and hence we can say that here, right, our this remains positive only if your population at any given time does not exceed a by b. Now, what we try to do here is we try to put here xn. Now, I am putting another variable here, xn to be equal to nn upon n maximum. Now, if you try to put this in this particular model, right, try to put this variable in this particular model, then that gives me an equation xn plus 1 is equal to, I am writing the constant, I am changing the constant of proportionality, although it would turn out to be a, but this happens to be alpha times xn into 1 minus xn. We find that the population dynamics, right, it observes sort of an equation or sort of a function, right, given in terms of xn, given in terms where xn plus 1 can be given in terms of xn. So, this follows a certain function, and that particular function is something which depends on x, and we call this function as the logistic map. So, we have the logistic map here. So, what I have here is that once I fix the constant of proportion alpha, I find this map to be f alpha x is alpha x times 1 minus x. Now, we are trying to study population, and when we want to look into population, of course, we can't study population if there is no species, then nothing can exist, and we can say that okay fine, we are sort of normalizing it. So, we say that the maximum possible population is 1 and the minimum possible population is 0. So, we try to study this logistic map in the interval 0 1. So, we study this, we study f alpha, right, in the interval zero 1. Also, we try to see that we will study this logistic map, right, maybe for alpha in the range of 0 to 4. Of course, what happens beyond 4 is something which you can easily analyze, but to start with we will study this for the constant of proportion to be from 0 to 4. So, what are we essentially studying here? So, we are essentially looking into, maybe this is the graph that we have of the logistic map. So, we have this logistic map here, and we want to study this for various alpha. So, we are looking in for alpha belonging to 0 4. So, when alpha equal to 1 we have this curve, when alpha equal to 2 we have this curve, alpha equal to 3 we have this curve, alpha equal to 4 we have this curve. Also, we observe that what is the derivative of f in this particular interval. So, we find that the derivative of f, that is f prime, f alpha prime of x happens to be equal to alpha times 1 minus x, right, minus alpha x. This is your derivative, and if I look into the second derivative, Yes. What should be the second derivative here? Minus 2 alpha. So, the second derivative here turns out to be minus 2 alpha. Also, we will want to look into, is there any possibility of a fixed point here? So, we are trying to look into what happens when f alpha x is equal to x. So, what kind of equation we are solving? We are solving this equation that x, right, alpha x 1 minus x is equal to 0, and what values does this give for x? So, one of the values one can easily take x common out of here. So, one of the values turns out to be x equal to 0, okay, which you can easily see from the graph that this is a fixed point here, right. And the other value which you can think of is, or I would put it up as alpha minus 1 by alpha. So, we have two equations, we have particularly two, we can have possibly we can have just two fixed points here by looking into the equation of the logistic map. We try to look into this particular case when my alpha is varying from 0 to 1. So, what happens when alpha is varying from 0 to 1? We look into this particular case here. Now, when alpha varies from 0 to 1, there is only one fixed point because my alpha is 1. So, the other fixed point was basically alpha minus 1, which did not exist in the interval 0 1. So, there is only one fixed point. So, we have only one fixed point. So, there is only one fixed point. And that fixed point is x equal to 0. And you can easily see this graph here, right, that this is the only fixed point x equal to 0. This is the only fixed point here. What happens to f alpha prime of 0? What is that equal to? So, let me again recollect, right, we have looked into this equation, right. If alpha prime of x happens to be equal to alpha times 1 minus x minus alpha x. So, what is alpha prime of 0 here? Yes, it is just alpha. So, this is just alpha, and hence we can say that our first observation here is that when alpha belongs to 0 1, right, this modulus will be less than 1. So, 0 happens to be, so 0 is a hyperbolic fixed point, and it is also a sink. What happens to alpha equal to 1? Now, when alpha equal to 1, 0 is a non-hyperbolic fixed point. Zero is a non-hyperbolic fixed point. So, we have to look into the case of non-hyperbolic fixed point. What is f alpha double prime at 0? So, we find here that f alpha double prime at 0 normally at x is equal to minus 2 alpha, right. So, this happens to be equal to minus 2, which is not equal to 0, right. And so, we can say that this point, right, 0 should be unstable. According to the theory, it should be unstable, right. But we observe here that what is the neighborhood of 0 that we are considering? We are considering values, right. We are considering the values only between 0 and 1, right. And in this neighborhood, but in the neighborhood of, in any neighborhood of 0, that is my neighborhood of 0 happens to be something like 0 epsilon, right. We find that f alpha prime at x is less than 1, f alpha prime decreases there, it is less than 1, And so 0, this fixed point 0 is a sink here. So, you can observe here that you start from any point here, right, you start from anywhere over here, fine, and you find that ultimately, right, the orbits are tending to 0. You can start from anywhere over here, ultimately the orbit is tending to 0. So, for alpha belonging to, for alpha taking any value between 0 and 1, right, there is only one fixed point 0. The dynamics is very simple, right, each and every orbit, each and every other orbit is tending towards 0. So, the whole set 0 1 can be thought of as a stable set of 0. Now, the case changes when my alpha becomes greater than 1. So, we look into this case alpha to be greater than 1. Now, what happens when alpha is greater than 1? Yes, we have another fixed point, right. So, when alpha is greater than 1, right, there is another fixed point . Let me call it x star, which is basically alpha minus 1 by alpha. So, we have this another fixed point here, right. What happens to f prime of f prime alpha of alpha minus 1 by alpha? What happens to this? What is the value of this one? What is the value here? We have f alpha prime x is alpha times 1 minus x minus alpha x. So, the value here turns out to be equal to 2 minus alpha. Now, this is 2 minus alpha. What is the value of f alpha prime x at 0, right? At 0 the value is certainly turning out to be greater than 1. So, the fixed point 0 now becomes a source. What happens to this value? Now, alpha minus 1 by alpha, so if I look into this x star, right. So, x star is a sink for mod of 2 minus alpha less than 1, right. If this holds true, then it is a sink. So, what happens in that particular case? So, if my alpha belongs to, now can think of this, if my alpha belongs to 1 3, right, in that particular case I will have this mod, this equation being satisfied. So, if alpha belongs to 1 3, then x star is a sink, whereas x equal to 0 is a source. So, I have two fixed points here, right, one is a sink, the other is source. So, if you start with any, say you start with any point here, right, ultimately this converges to the fixed point x star, right. What happens when alpha equal to 3? So, we are essentially looking now what happens to alpha equal to 3. When alpha is equal to 3, we find that f alpha prime of alpha minus 1 by alpha, what does it turn out to be? Minus 1. So, this point x star is now a non-hyperbolic fixed point, and since this is a non-hyperbolic fixed point, we now look into again what is f alpha double prime, right, at alpha minus 1 by alpha, which basically is my minus 2 alpha, and my f triple prime f alpha triple prime at alpha minus 1 by alpha, that happens to be equal to 0. So, we find that when alpha is equal to 3, this fixed point x star is a non-hyperbolic fixed point, but for this non-hyperbolic fixed point we find the derivative to be equal to minus 1, right. So, we now need to look into the Gaussian derivative of f alpha at this particular point, and we find that this Gaussian derivative of f alpha, right, at this particular point alpha minus 1 by alpha is less than 0, because this term is missing, right. So, this quotient derivative is less than 0. Since this quotient derivative is less than 0, so this fixed point x star equal to alpha minus 1 by alpha, right, is a sink. So, we find that this happens if this turns out to be a sink. Now, interesting case is what happens when alpha becomes greater than 3. So, we go to the next case, what happens when alpha is greater than 3. So, essentially we will be looking into this case that my alpha belongs to 3 and 1 plus root 6. So, we will say this alpha being greater than 3. Now, what happens when alpha being greater than 3? Once alpha is greater than 3, we have already seen what happens to the fixed point. 0 is already a source, right, and now even x star becomes a source, right, because modulus becomes greater than 1 there, right. So, we find that x star happens to be, so this attracting fixed point now becomes repelling. But we try to observe some particular orbit over here. So, let me take for any point say x here, let me try to look into what is its orbit here, how does its orbit behave, then this goes to what we observe here is that you start with any typical orbit, then it basically starts oscillating around this fixed point x star, right, giving us a kind of period 2. So, what happens here is that this observation gives us, so it settles down between 2 points, it is basically oscillating between 2 points and then settles down in these particular 2 points. So, maybe we can think of another orbit here. So, let us try to look into this particular orbit. So, we find that here it comes back here, right, goes back here, goes back here again, goes back here, and then again it settles down to this 2 orbit. So, what happens here is this indicates the appearance of a period 2 orbit. Now, if really there is a period 2 orbit, we should be able to solve the equation, right. If alpha x square equal to x, and what essentially that means that if I am looking into alpha x times 1 minus x into 1 minus alpha x times 1 minus x, this should be equal to x. So, if I try to write down this equation, right, I know that this equation, trying to simplify this equation, I definitely have x common, right. I can also say that x minus alpha minus 1 by alpha is another common part, and the third part I see this is alpha square x square minus alpha times alpha plus 1 into x plus alpha plus 1, this is equal to 0. So, you can simplify this equation in this particular form. Now, we already know that we have this fixed points, right, alpha minus 1 by alpha and alpha and x equal to 0, right. So, these are definitely going to be the fixed points for if alpha square x equal to x, they are going to be fixed points for that also. So, what we get is we get another set of fixed points over here which come up from this particular equation. Now, if we try to solve this particular equation, then the solution of this particular equation gives us, right, 2 points x1 x2, which is we can write it as alpha times alpha plus 1 minus I have this root of, maybe I should write it as alpha square into alpha plus 1 minus I have 4 times alpha square times alpha plus 1. It should be plus and minus here because I am looking into both x1 and x2, and then divided by twice alpha square. So, now if I try to look into this part, if I try to solve this particular say this equation, then simplifying it we get that this happens to be alpha times alpha plus 1 plus or minus root of, now I have an alpha here, maybe I can cancel this alpha out. So, this is just alpha plus 1. I have alpha square here which comes out and becomes alpha, and there is an alpha in the denominator which can be cancelled out. So, what we get here is, we just simply get here is alpha plus 1 plus or minus alpha plus 1 into alpha minus 3, right, divided by 2 alpha. So, I get that x1 and x2 happen to be equal to alpha plus 1 plus or minus under root alpha plus 1 into alpha minus 3 upon 2 alpha. Very easy to see from this equation that this x1 and x2 will exist only when alpha is greater than 3, right. So, only when alpha is greater than 3 we have this x1 x2 existing, and when this x1 x2 exist, right, we can now think of what happens to the dynamics or what happens to this particular period 2 orbit. So, we see that, right. So, only when alpha greater than 3 exists, and now we can look into the dynamics. So, what happens at alpha square, right, I am looking into this prime at the point x1, right, and by symmetry this will be same as f alpha square prime at x2, which happens to be same as f alpha prime x1 into f alpha prime x2, and what is that equal to? Now, we want to say that we will have this happens to be a hyperbolic periodic points, right. So, this periodic orbit is hyperbolic when we have, so for this I have f alpha prime x1 times f alpha prime x2, right. I should have this to be less than 1. This basically gives me a sink there, right. So, if this is less than 1, what do we want? We want it to be less than 1. So, basically if I look into this equation, this basically means that minus 1 should be less than or less than, basically I should say this is less than 1. So, minus 1 should be less than, now I am multiplying the 2 and we know what is the derivative here. So, the derivative here turns out to be alpha times 1 minus x minus alpha times x. So, the derivative, if I look into that aspect, I can say that this derivative I can take alpha common here. So, I have alpha square times 1 minus twice x1 into 1 minus twice x2, and I want this to be less than 1. I can push in the value of alpha 1 and alpha 2 here. So, that gives me minus 1 is less than alpha square. I have 1 minus, right. So, I can write this as alpha plus 1, right, plus root of alpha plus 1 into alpha minus 3 divided by alpha into again 1 minus alpha plus 1 minus root of alpha plus 1 into alpha minus 3 divided by alpha. So, this particular part should be less than. Now, think of this part, if I try to simplify this once again, I have an alpha coming up over here. So, I have alpha minus say alpha plus 1. So, I have an alpha coming out here, I have an alpha coming out here. So, this alpha square gets cancelled, right. Then what I have is alpha minus alpha plus 1, which essentially turns out to be equal to minus 1, right. This turns out to be minus 1, right, and then I am multiplying this two facts, right. So, what I get here is, just simplify this factor, I get that this is less than 1 minus alpha square plus 2 alpha plus 3, and I want this to be less than 1. Again simplify this once again, what you get here is that minus 1 should be less than minus alpha square plus 2 alpha plus 4, and that is less than 1. Exactly this is satisfied when my alpha belongs to, so this basically this is satisfied when my alpha belongs to, of course it should be greater than 3 and goes up to 1 plus root 6. This is satisfied for these values of alpha. So, whenever my alpha lies between 3 and 1 plus root 6, we find that this periodic orbit of period 2 happens to be a sink. So, everything, all the orbits in 0 1, right, excepting for these two, the two fixed points are definitely there as it is, right, but then these two fixed points are sort of source, right. So, they are repelling, but all the other orbits are attracted into this particular periodic orbit. So, you have this periodic orbit and every point is attracted to this periodic orbit. What happens when alpha equal to 1 plus root 6? So, we shall look into that particular case. So, let me look into the next case. What happens to, so this is my fourth case, what happens when alpha is equal to 1 plus root 6? What happens in this case now? So, if I look into what is f alpha prime of x1, right, into f alpha prime of x2, we know what is that multiplication here, right, and in that particular case it turns out to be equal to minus 1. So, now we have that this periodic orbit is non-hyperbolic, right, it is a non-hyperbolic periodic point, and for this point, so this orbit, so I should say that periodic points are now non-hyperbolic What is this quotient derivative of f alpha at this point x1? Of course, we want this f alpha square, right. So, this quotient derivative at this particular point x1, right, and if you look into this quotient derivative of f alpha square at this particular point x2, we again find that this is less than 0. The simple reason being we know that the triple derivative happens to be equal to 0, right. So, this quotient derivative is less than 0, and so these periodic points are again attracting. So, they form a sink. So, this periodic orbit forms a sink, and so they are attracting. So, x1 and x2 are again attracting. But what happens now when my alpha is greater than 1 plus root 6? We find that these periodic, with this periodic orbit becomes a source. They are non-hyperbolic now, sorry, they are hyperbolic now, for alpha greater than 1 plus root 6, they are hyperbolic now, and now they become a source, right. So, when alpha is greater than 1 plus root 6, these periodic points they become repelling. So, they are repelling. Now, if they are repelling out, that means the orbit is going somewhere else. So, what happens to this orbit? We try to look into this fact again. So, what happens when alpha becomes greater than 1 plus root 6? So, we will look into this next case. So, what happens when my alpha goes beyond 1 plus root 6? These two periodic points are basically these two are repelling. So, we find that there is another periodic orbit of period 2 square, period 4 bond, right. So, a periodic orbit now we have a new periodic orbit. So, again for this new periodic orbit we find that under certain conditions this is attracting, this is a sink. So, all the nearby orbits are basically being attracted to this. We do have our fixed points as it is, we do have our period 2 points as it is, but these are source. So, they remain where they are, all the points etc., every other point, every other orbit is being attracted to this periodic point of period 4. Now, if we proceed in this manner, we try to see what happens here in this particular case. So, we see what happens here is, if you look into the graph of x versus alpha, from as alpha varied from 0 to 1, we had only one fixed point 0, and that particular fixed point 0 was the only attracting. So, what happens at infinity, when you try to see what happens at infinity, you will see that the system is only turning out to be equal to 0. So, the entire thing is collapsing to 0. So, we can only see 0 here, we can't see anything else at infinity. What happens when your alpha varies from 1 to 3? So, as alpha varies from 1 to 3, you find that there is only one fixed point which is attracting, and that fixed point is basically, you can say that this is your alpha minus 1 by alpha. So, alpha minus 1 by alpha is the only fixed point, right, which is attracting. So, at infinity you can see only this fixed point, because all other orbits would have collapsed to this particular fixed point. And then what happens at 3? So, once you go beyond 3, there is a new periodic orbit of period 2 bond, and once you have a periodic orbit of period 2 bond, this periodic orbit is sense of attracting, right. This loses the stability. So, this fixed point is definitely there, but now you cannot see this point, because this point has lost its attractive nature, right. So, what you find is, you find only periodic orbit of period 2, and this goes on till 1 plus root 6. So, in 1 plus root 6 you find that this periodic orbit also loses its attractiveness, right, it becomes a source here. And so, what you find is that there is another period 4 bond here, right, and this period 4 becomes attracting. Now, we find that this continues till maybe approximately the value of alpha being 3 plus 3.57. So, we try to look into this fact, so 3.52. So, we have this alpha, so this continues. So, what we find here is that whenever your 1 plus root 6 is less than alpha, is less than, I am looking now this to be approximately something like 3.54, right. So, we have this periodic orbit of period 4 bond. Now, what happens is, this periodic orbit of period 4 again becomes repelling, right, when alpha increases beyond 3.54. So, once alpha is greater than this quantity, it again becomes repelling. Now, what happens in that case? Now, again you find that there is another periodic orbit of period 8 coming up. So, the period 4 orbit becomes unstable, but there is another periodic orbit of period 8 coming up, which again becomes stable. So, as alpha increases, we find that periodic orbits of higher order. Now, when I talk of higher order, this is according to the Sarkowski's order. These are born, and then they eventually become stable, right. So, you have these are born. So, this happens, say, orbits of period 2 square, 2 cube, 2 4, etc. These are born, and then they eventually turn repelling, then new orbits are born, right, which become attracting and so on, and this goes on approximately, so this goes on, I am looking this to be approximately till your alpha star, I am looking into this value of alpha star happens to be 3.62. I am just saying that this happens approximately till 3.62. Now, what happens beyond that? So, what happens beyond that? We will try to look into this picture. So, let us look into the next case and maybe then we can go to the picture. So, what happens beyond that? So, if we look into now the sixth case, right. So, I am looking into alpha to be greater than alpha star. What happens in that case? Alpha at alpha star equal to 6.32, right. We find that there is a periodic orbit. So, here we find a periodic orbit of period 6 is born. So, we find again periodic orbit of period 6. Now, 6 is, as we know, it is an even number and this is the greatest even number in Sarkowski's ordering. So, we find that this periodic orbit of period 6 being born, once it goes beyond this, again there is lot of sort of kind of chaos, you can think of that part, right, and the orbits become more and more complicated and we find that again we have sort of new periodic orbits being born, this is again going on, right, new periodic points being born which are attracting, right, and the earlier ones they lose their attractiveness, so they all become repelling. So, one is so we get more and more stuff, right, till this goes. So, new periodic points of higher period in the Sarkowski's ordering are born, and this goes on till my alpha reaches the value 1 plus root 8. Now, what happens at 1 plus root 8? When alpha equal to 1 plus root 8, I should say an attracting of period 3 is born. An attracting periodic orbit of period 3 now is born, and we know that 3 is the highest largest number in Sarkowski's ordering. So, once we have this attracting orbit, we see that everything is tending to up. So, the entire we have periodic points of all periods now, and all these periodic points are sort of repelling, and the only point which is attracting, the only periodic orbit which is attracting is this periodic point of period 3. So, periodic point of period 3 is attracting and it is attracting all the orbits over there. So, all you can see is this periodic point of period 3, and what happens beyond that? So, we find that what happens beyond that is when your, maybe I should call it the 7th case, right, when alpha becomes greater than 1 plus root 8. Now, this when alpha becomes greater than 1 plus root 8, this periodic orbit of period 3 also becomes repelling. Now, you have a very terrific case here that you have so many you have periodic points of all periods and all these periodic points are repelling. So, what happens to the orbit there? So, you find that the orbit of a typical point never settles down anywhere, it just keeps on wandering, right, throughout the interval 0 1. So, all periodic points are repelling here. And what happens here is all orbits I should talk of other orbits, because periodic orbits definitely have a definite motion. So, all other orbits keep wandering. And I should say where, so it keeps wandering throughout 0 1, right. All other orbits keep wandering throughout 0 1 and they do not settle anywhere. And this typically happens, since we are looking into the case, we are looking basically into this case when 1 plus root 8 is less than alpha and this is less than or equal to 4. So, we stop at this case 4 here, because ultimately what happens when the case is greater than 4, when alpha again turns out to be greater than 4, is exactly what happens at alpha equal to 4. So, there is actually no change in the scenario there, and we find that the orbits keep on repelling. So, if we try to sum up whatever we have done till now, whatever we have observed till now, maybe we will look into this particular picture. So, we try to analyze this particular picture here. So, here we find that you have a periodic orbit, right. Maybe I should take up this blue. So, up to 3, right, up to from 0 to 1 you had this periodic orbit, 0 was stable, right. Then you have another fixed point bond and that is stable, and that goes on till your alpha reaches 3. At 3 you find that there is a periodic orbit of period 2 bond, right. So, there is a periodic orbit of period 2 bond here, and what you find is that up to from 3 to 1 plus root 6, this particular periodic orbit is stable. So, when you look into the dynamics, what happens at infinity, right, only this stays, this orbit stays, nothing else stays, right. And what happens at 1 plus root 6? At 1 plus root 6 you again find that this is now repelling and there is another attracting periodic point of period 4 being bound, and this continues till, as we had looked into the case, some 3.54 or, right, and there we find that again there is another periodic point of period 8 being bound and so on. So, this period doubling, right, we can say that there is a period doubling going on. So, this period doubling goes on, right, till maybe you are looking into the case of something like 3.6 here, right, 3.6 something here, where you have a periodic point of period 6 being bound. So, you have a periodic point of period 6 being bound here, right, and once you have a periodic point of period 6 being bound, the period no longer doubles, right, because we have now we basically have periodic points of all even periods, the period does not double, but still there are new and new periodic points being born, and now these periodic points are basically periodic points of odd order, right. So, or odd periods. So, that they keep on being born till here, where you can find a periodic point of period say 7, right, whereas here you find a periodic point of period 5, and ultimately at 1 plus root 8, right, you find a periodic point of period 3. So, once you reach this point of period 3, you see that the dynamics becomes like you can almost see that almost every point is covered up over here. So, the full 0 1 is realized over here, right. So, as and when you reach 4, of course, till you do not reach 4 the map is not onto. So, you find that everything is realized over here, and as you reach 4 you find that every single point is taken up by the orbit. So, if you try to look into the dynamics what happens at infinity, you find that every point in 0 1 being taken up. So, the population and now you can think of this in terms of the population. So, the population becomes sort of very stable here, right. So, if I look into alpha equal to 4, my population is very stable in the sense that it exactly remains the same, though there is lot of dynamics going on. We have this interaction also, we have the population decrease due to interaction also, but in all cases the population becomes as such, it becomes stable, it looks the same, right, because you have that it is taking up each and every value, right. I hope this is clear to all of you. So, today we stop here.